Hi all, welcome to another video of compressible fluid flow video lecture series. In the last class, we have discussed about two important terms called bulk modulus of elasticity and coefficient of compressibility, K and beta respectively. And we have discussed about the importance of those two parameters of those two terms in wave theory, which is also very important concept for the analysis, for the proper analysis of compressible fluid flow problems. Now, what is wave theory? We are all familiar with this theory. We have studied this way back in our plus 2 physics. But the difference here we are also learning about this wave theory. But the main difference is we are now dealing with fluids, or specifically we are now dealing with compressible fluids. Okay, previously when we have studied wave theory, we have considered the wave propagation in solid only, but now we will consider the wave propagation of the fluid, wave propagation in the case of a compressible fluid. That is the main difference of the wave theory which we have studied and now we are going to study. So, wave motion, it is actually the movement of disturbance relative to the medium. It is the movement of disturbance in the medium, and the wave motion is the relative motion of the disturbance in the medium. Okay, so for the disturbance to be produced, there must be a source of disturbance. So from the source, the disturbance will be moving in the form of wave. Okay, that is the wave theory we have studied in physics. Now, this special phenomenon, we need to consider in the case of solid also, for just familiarizing the term for just familiarizing the wave theory, we will consider the wave motion of the solid first, then we will move to the compressible fluid case. So in the case of solid, when a wave propagation occurs, the disturbance will move from one point in the medium to the another point in very less time. In the case of solid, it will take very less time. The time required is very small in the case of solid, but in the case of fluids, or in the case specifically in the case of compressible fluid, there will be a departure of the incompressible flow to the compressible nature when we consider the wave motion. Okay, we need to analyze that departure, when this departure will occur from the incompressible flow to compressible flow in the case of a fluid. That will be explained in this talk. Now, when compressible fluids are considered, there are different types of waves associated with this wave theory, and the waves under considerations are infinitesimal pressure wave, which is also known as sound waves, non-steep pressure waves with finite amplitude, steep pressure wave, which is known as shock wave, and a final type is called expansion wave. Okay, now we will discuss all these four types of waves in detail in the coming topics in coming modules. But before that, let us look into two important types of waves, which is shock wave and expansion wave, or compression wave or rarefaction wave. What are the difference between these two types of waves? So the first one, a wave which is at low pressure than the fluid into which it is moving is called an expansion wave. Okay, the wave with low pressure of the fluid is called expansion wave. In that case, expansion takes place. In the expansion process, pressure will decrease. We all know that. This wave is also known as the rarefaction wave. So when this wave has passed, the pressure at a particular region will decrease. Okay, that is the nature of this expansion wave. Conversely, a wave which is at high pressure than the fluid is referred to as compressive or compression wave. This means when this wave has passed, the pressure at the region where this wave has passed will become higher. The pressure value will increase. Temperature value will also increase after this wave has passed through a particular medium. Okay, this wave is called compression wave. We all know that after compression process, the pressure value and temperature value will increase. Just like that, when this wave is passed, the pressure value and temperature value will increase in that particular region. Okay, That is called compression wave. An example for compression wave can be we can relate this with bomb explosion. When a bomb is exploded, a pressure wave will be generated. A series of pressure waves will be generated, which will be increasing in radius. We have seen in movies, right? It's the radius, the explosion radius will increase. That means the radius of the wave will increase. But when this wave is passing through the regions or the region through which the wave has passed, will be undergoing devastation and destruction. Okay, we have seen this in different movies. So these waves are generally considered to be very destructive because it will increase the pressure and temperature. That's why the destruction is taking place when a bomb explosion is taking place. Okay, so just connect this idea with the bomb explosion. Now, wave propagation in an elastic solid medium. Here we are considering, actually in the wave theory, we are considering only about compressible fluid flow. But for the easy comprehension of this wave theory, we will initially consider the wave propagation in the case of an elastic solid medium. Then only we will go to the case of compressible fluid flow. So just look at this example. A metallic rod is taken. This is actually the front view of a metallic rod, and L, small l is the length of the rod, and A, capital A is the cross-sectional area of this solid medium. Okay. Now, a compressive stress is applied on one end of this rod, and this compressive stress is denoted by small f. Okay, small f, Newton per centimeter square. That is a unit of this small f. Don't confuse with capital F. Capital F is taken as force. Here we have force by area. We have denoted by small f. So this small f is its unit is newtons per centimeter square, or newton per millimeter square, or meter square. Okay. So this is a compressive stress. Now, as a result of this compressive stress, when we have applied this compressive stress at one end of this rod, metallic rod, a wave will be generated. Okay. Uh, this wave can be considered as any type of the wave. For the time being, we can consider this wave as a compressive wave. Okay, so this wave will be traveling from this left side to the right side of this rod. So now in this diagram, the wave has reached at this position. Okay, so the wavefront is the moving wave. Wavefront is called a moving wave. The wavefront shown here is actually the current position of the wave, which has moved from the left side, from this side up to this side. Okay. So what all changes have occurred in this rod, metallic rod, after giving this compressive stress at one end of the rod? Now we will look into that in the next slide. So the same diagram has been shown here. The figure shows a solid rod of uniform area of cross section capital A. Now the compressive stress F, newtons per centimeter square, or newton per millimeter square, or newton per meter square. Okay, that is generated due to the sudden action of a force at this end. And the distance traveled by the wavefront with the velocity a in time t is at. That means this wavefront is traveling from this end to this end. Now it has reached at this position, so it has a velocity. The velocity of this wavefront is considered to be small a. Small a is the velocity of this wavefront, and it is traveling at a distance at. That means after time t, it has traveled a distance a into t. If a is the velocity and t is the time, we can find the distance by velocity into time. By that relation, we can show the distance traveled by the wave after time t as a into t. Okay, that is at. So this distance shown here is the distance traveled by the wave, a into t. Now the change in the length of the portion of the road through which the wave has traveled. Now after applying this compressive force, the wave is created and the wave has propagated from this point to this point. but there is a change in length of the portion of the road. The road length has been decreased after the application of this stress. So the change in length is delta L. Delta L length is reduced from small l. So the change is L by L minus delta L. L minus delta L is the final length of the road after the propagation of the wave. So that's why it is called a compressive wave. Okay. Now, therefore, the strain value. We have the change in length by the original length. We will consider the length up to which the current position of the wavefront only. Therefore, we will not take the entire length L. Now the wave has traveled only up to this point. So the length up to which up to the current position is 80. We have discussed about this before. 80 is the current length of the road up to which the wave has traveled. So that is the original length that has been taken as the original length. Therefore, the change in length is delta L. Therefore, strain is change in length by original length delta L by original length 80. Now, modulus of elasticity of the rod, capital E, it is stress by strain. Our stress value is F, newtons per centimeter square, divided by strain is delta L by 80. Okay. Now, again we are considering the same diagram. We will find the particle velocity of the medium. Here, there is a change in the length of the rod. That means the medium particle has traveled from this point to this point at a distance delta L. So there is a velocity for the particle medium also, that is the rod material also, that is delta L by T. After T time, the wave has reached to this position, but our particle has reached only up to this distance. So delta L, distance by time, delta L by T is the distance traveled by the medium, which is denoted by small c. Now, our small c can also be written like this, F by E by A. Okay, F by E by A. Applying momentum equation to the above system. Okay, this change is got by comparing this relation with the previous relation. We have already derived like this, E is equal to F divided by delta L by 80. Okay, now we have also derived C is equal to delta by T. That means E is equal to F by C by A. That means C is equal to F by E by A. We can change that relation like this. So now we have obtained a relation for the velocity, medium velocity. Now applying momentum equation to the above system. Momentum equation is like this, impulsive force is equal to change of momentum. Now impulsive force means force into time. Impulsive force is force into time. So to get force, we have multiplied area with the compressive stress F into A and into time, force into time. For that we have multiplied with T, and change in momentum is rho into A into AT into C. That means AT is the distance traveled by the wave. So distance into area is the velocity. Distance into area is the volume, and we have mass per volume as the density. So this volume will get cancelled, the volume from the density, and this area into distance volume get cancelled, and we have mass into velocity. That is a momentum. Momentum is mass into velocity. Okay, therefore impulsive force is equal to change of momentum, and from this relation we will get C is equal to F by rho A. Now we have two relations for C. Equating those two relations by comparing those two equations, we can equate F by E by A is equal to F by rho A. That means E is equal to rho A square. That itself means A is equal to root of E by rho. This can be considered as a final relation between the wave velocity and the elasticity, modulus of elasticity and the density. This is a very important term when we are considering the wave propagation in a solid medium. Okay. Now we will consider the solid we will consider the wave propagation in sound in the next video.